Hi everybody. So in today's video, which is our AP Review second video, we're going to be reviewing some vocabulary about graphs and some of the different types of free response questions that you might get asked that's related to analyzing the behavior of a function on a graph. So we're going to start with just some review vocabulary words. And one of the reasons we're reviewing this is that oftentimes the definition of the word is how you justify your answer. So, for example, a critical point on a graph is the place where the derivative is equal to 0 or does not exist. So we're talking about the first derivative being equal to 0 or does not exist. Now, it's really important to know that that's the definition. And the reason that it's important to know that that's the definition is because if we were asked to justify our answer for why a certain value was a critical point, we would say because f prime of x is equal to 0 or does not exist. If we were looking for where a function was increasing, that means it's the intervals where f of x has a positive slope. Now, when we're writing these intervals, we always use closed brackets for all of our intervals for increasing, except for, of course, if one of our numbers is infinity. So in this case, our f prime of x would be greater than or equal to 0. And again, if we're asked to justify our answer, we would say because f prime of x is greater than or equal to 0. If we were looking for where a function was decreasing, we would say that these are the intervals where the original function, f of x, has a negative slope. And again, for this type of answer, we would always use closed brackets, unless, of course, we had an infinity. If we were looking for our definition and how we would justify our answer, we would say because f prime of x is less than or equal to 0. Now, all three of these pieces of information have to do with the first derivative. Is the first derivative equal to 0 or does not exist? If the first derivative is positive or if the first derivative is negative would be these definitions and how we would justify our answer. However, the second derivative also gives us information about a graph. It just tells us different information. So a point of inflection is a place where the second derivative changes signs. Now, it's important to note that in order for the second derivative to change signs, you're going to look for the places where the second derivative is equal to 0 or does not exist. And then you would make a signs chart if necessary, to see if the concavity actually changes there. So what makes a critical point and a point of inflection different is that in order to be a critical point, all you have to do is make your first derivative equal to 0 or does not exist. It doesn't matter if the first derivative actually changes signs there. However, to be a point of inflection, it does matter. In order to be a point of inflection, the second derivative has to actually change signs. Now, along with looking at the second derivative for points of inflection, we can also look at the second derivative to determine the concavity of a function. Now, as a reminder, concavity is really just another word for curvature. So in addition to looking at whether the slope is positive or the slope is negative, we want to look at whether the slope is curving up or curving down. Concave up, we always say looks like a cup, and concave down, we always say looks like a frown. So in this case, the definition of concave up would be the places where the second derivative is greater than 0. If we were going to justify our answer here, we would say because the second derivative is greater than 0, or in cases where we don't have the second derivative, we could say the first derivative has a positive slope. So, in cases where you cannot find the second derivative because you don't have a function to use, for example, let's say you were just given a graph of f prime, you would look at the slope of that graph because the slope of the first derivative is the second derivative. Now, if we're talking about concave down, we're looking at places where the second derivative is less than 0, or if you can't actually find the second derivative, so if, for example, you don't have a function, you just have the graph of f prime, we would say it's because f prime has a negative slope. Now, again, all of those ideas are tied to the second derivative. And what we do is we take all these ideas and we put them together to help us analyze features of a function. And some of the other key features that are usually important to our analysis are relative maximums and relative minimums, and absolute maximums and absolute minimums. We call those absolute extrema. Now, a relative minimum and a relative maximum must occur at a place where the first derivative is equal to 0 or does not exist. And for a maximum, f prime of x changes signs from positive to negative. If you were to picture a maximum in your head, you can kind of visualize that the slope is going to be positive, changing to negative, and that's what makes it a maximum. For a relative minimum, it's going to be a place where the first derivative is equal to 0 or does not exist. In other words, it has to be a critical point. But more importantly, the first derivative has to change from negative to positive instead of from positive to negative. So your wording of your answer here is really important because how the signs change determines whether you have a max or a min. And if you picture a minimum in your head, you can kind of visualize that there would be a negative slope changing to a positive slope. I'm going to back up for 1 second. I just realized I forgot to write that for concavity, we always use open parentheses. Always. We don't ever use closed brackets. I apologize. I'm just going to back that up for 1 second. All right, now moving forward. Absolute extrema, so absolute maximum and absolute minimum, are a little bit different because now, in addition to considering the critical points, so the places where the derivative is equal to 0 or does not exist, we also have to consider the endpoints. Now, for relative max and relative min, we don't include the endpoints. We don't have to worry about where the function starts and stops. However, for absolute extrema, we do need to consider the endpoints. So it's important to remember that in addition to finding the places where the derivative is equal to 0 or does not exist, we also need to look at the endpoints of the function. Then you're going to make a table of values. Now, your table of values should look like a regular old XY table, where you would use this for a function to graph it. In this table for the X values, you're going to include the critical points and endpoints. To calculate the y values, you're going to have to use a variety of techniques related to understanding how to find the original function when you have the derivative. All right, so moving forward, there are two different applications where we typically see these types of questions. So in addition to understanding this vocabulary, here are a few more things that are going to be tied together with analyzing a function and analyzing a graph and the features of a function. The first thing that's often tied into an FRQ with these ideas is the fundamental theorem of calculus. Now, the fundamental theorem of calculus basically says that derivatives and integrals are opposites. So if we have f of x equal to the integral from 2 to x, these types of functions, where your function is defined as the integral of a different function, these are what are called accumulation functions. because the function f of x is the integral of a different function. Oftentimes, we are asked to analyze f of x using these ideas. What are the critical points? If it's increasing, if it's decreasing, concave up, concave down. In order to do that, we're going to need to take the derivative of f of x. Now, as a reminder, the fundamental theorem says that if you take the derivative of f of x, which is the left side, then you just need to take the derivative of the right side of the equal sign. And when you take the derivative of an integral, the derivative and the integral are opposites, so they essentially cancel, which means we just get g of x. The only change that happens here is that you end up dropping the x, whatever the bound is, into the equation. Now, if one of your bounds is just a number, you don't have to worry about that because the derivative of a number, remember you're taking the derivative, so the derivative of a number is 0. We don't have to worry about that. You're often also going to need to find the second derivative. So the second derivative, which would mean taking the derivative again, would just be g prime of x because the derivative of g is g prime. Now, this is what I would consider a relatively simple example. They do get a little bit more complicated. So as a reminder, if we were to take the derivative in this equation, the reason this is a little more complicated is that our bound is a 4x and not just an x. We would still drop in the bound, but now we need to incorporate chain rule. Now we're going to do the chain of whatever we plugged in, which in this case would just be 4. So your derivative is not just g of x, it's g of 4x times the derivative of the bound. Now if you were to simplify that, that would be 4g of 4x. Just put the 4 at the beginning. Now that does also kind of complicate the second derivative. So the second derivative here would be 4g prime of 4x. And then we need to multiply by 4 again because again we're doing chain rule. So in the end here, your second derivative would end up being 16g prime of 4x. Now, one last reminder. Oftentimes in these questions, students try to just memorize that f prime is just going to be g and f double prime is going to be g prime. The mistake you're making here is that there are subtle changes to what has to happen with your derivatives depending on the original function. So this type of question right here is very typically a question where we see mistakes among our students. And here's why. A lot of students want to go like this. The derivative is just g of x, just drop in the bound. What they're doing is they're forgetting about this 6x. The derivative of this function is the derivative of 6x plus the derivative of the integral. Now the derivative of 6x is just 6, plus the derivative of the integral would just be g of x. Oftentimes, I see students just say f prime is equal to g of x because they're forgetting about that 6x at the beginning. Now, when we take our second derivative, the derivative of 6 is 0. So that's not going to be part of our second derivative. It's not going to be affecting our answer, and we're just going to have g prime of x. One other idea that often comes up that is related but not always directly part of these questions up here where we're analyzing our function is finding function values. So finding the value of the original function using the derivative. An example of this type of question would be, suppose that you know that f of 2 is equal to 3, and you have a graph of f prime. Find f of 6. Now, in order to do this, we need to really go back to the definition of a function. And we can relate this back to what we talked about when it comes to like position, velocity, and acceleration also. If you want to find the value of a function, then you need to take the starting value plus the integral from the initial x value to the specified x And inside of here, we put our derivative. For this particular problem, that means it would look like this. F of 6, the number we're trying to find, is going to be equal to my starting y plus the integral from my starting x to 6 of f prime of x dx. Now we can think back to how we calculated, for example, position. If we had velocity, we did the initial position plus the integral of velocity. You're essentially taking where you started and adding in the displacement to find out where you are now. What I'd like to do now is go through kind of two typical prompts. Now, I'm not going to actually do these problems with you. What I want to practice doing is familiarizing ourselves with what these questions look like. Practice reading the instructions, because one of the things that's really important about the AP test is that the directions give you a lot of clues about how to do the problem. And also looking at the specific questions, because again, in the question, in the wording, are clues about how to do the problem. And then finally, we will go through some hints for success in order to do these problems. So let's start with the first kind of typical question that we see. The first type of question that we see that's related to analyzing a graph of a function is if we are given the graph of the derivative function. So in these problems, we're not given the graph of f of x, we're given the graph of f prime. And it's really important to realize that. So what I'd like to do is start by reading through this prompt. So just what do the words say and what are they telling me I should pay attention to? It says the figure shows the graph of f prime. So f prime, this is really important. This is the first thing that needs to jump out at me. And if it's not already labeled on the graph, I'm going to go label that really large, because I need to remember that this is not the original graph. This is the graph of the derivative of f. It says for -7 is less than or equal to x is less than or equal to 7. In other words, this graph starts at -7 and stops at 7. Obviously, one of the things that comes up a lot when you're writing intervals is, does it go to infinity? Does it stop? What happens? By telling you that it's set on this interval, it's telling you there's an end point here and there's an end point here. It doesn't keep going forever, it stops. The graph of f prime has horizontal tangent lines at -3, 2, and 5. So what does it mean to have a horizontal tangent line in these three places? A horizontal tangent line is a place where this graph has a slope of 0. So right here, the slope is 0. Right here, the slope is 0. And right here, the slope is 0. Now that's important because oftentimes we're going to be looking at sections of the graph. For example, this section of the graph is going downhill. This section of the graph is going uphill. This section of the graph is going downhill. And what this is telling me is that you don't have to guess. The graph changes from downhill to uphill in those three spots. It also tells me that I have a vertical tangent line at x equals 3. In other words, right here, you can see the graph goes vertical for a second. And that's my clue that if the number 3 is ever a portion of my interval, so for example, if I was ever going to look at this chunk of the graph from 2 to 5 and 3 is in the middle, I need to be careful because the slope there is undefined. So if I'm looking at the slope and I'm looking at that section of the graph, I'm not going to need one section, I'm going to need two sections, because this is a spot where the slope is undefined. So I would not be able to include it within my interval. So again, reading the directions is really important. It's telling me, it's giving me clues that, hey, if 3 is involved, you better pay attention. And you know what? Don't just guess where it changes from uphill to downhill. Here is where it changes from uphill to downhill. For part A of this prompt, it said, for find all the values of x for -7 is less than x is less than 7, at which f attains a relative minimum, and justify your answer. One of the habits I want you to start getting into is breaking down the question into its parts. So every question usually has multiple parts to your answer, and you want to make sure that when you're doing your work and when you're circling your answers, you indicate that you've completed all portions of the question. So the first part of this question is find all the places at which f attains a relative minimum And the second part of this question is to justify your answer. If I'm taking the test, especially this year where I'm at home and I have highlighters and pens and whatever, I'm going to make sure that I indicate I've done both parts of that question. However, there is one hidden clue here. Your hidden clue here is that it says specifically for -7 is less than x is less than 7. You'll notice that there's no equal to. That is the test, the question writer's way of reminding you that for relative minimums and relative maximums, we don't look at the endpoints. Whereas for absolute maximums and absolute minimums, we should consider the endpoints as potential candidates. Now, by contrast, if you look at part B, where it says, where does f obtain an absolute maximum, you're going to notice that when they wrote this interval, they did include the underline. So this one is telling you don't consider the endpoints. Just as a reminder, in case you forgot, guys, the endpoints don't matter for relative mins and maxes. That's what the question is telling you. Whereas for this question, where there is an underline, they're telling you, hey, hint, hint, guys, if you forgot, you need to consider the endpoints here. And again, this is a question with multiple parts. There's where is the absolute maximum? And there is the justify your answer part of this question. So if I'm taking this test, I'm going to go back and make sure I've answered both parts of the question before I submit it. Part C is another typical question. It says, find the open intervals on which f is both increasing and concave up, justify your answer. So the question here is to figure out where my function is increasing and concave up, which means there's two qualifications. So increasing would mean where the derivative is positive, so above the x-axis. Concave up would be having a positive slope because that's the second derivative, which is the slope of the first derivative. So you'd really be looking at this portion and this portion of the graph between -1 and 2 and between 5 and 7. However, there is one hidden clue here, just like in the other problems. It says find the open intervals. Open intervals means your answers should use open parentheses and not brackets. Students often get confused. Increasing is brackets, concavity is open. Which one do I use here? The question is building in an answer to that. So if it says open intervals, you better make sure your answers have always got open intervals. You also want to make sure you justify your answer. Now, when you justify your answer, your justification should have two parts because you need to justify why the sections that you named were concave up and why those sections that you named were also increasing. So all at once, they should be both increasing and concave up, and you need to justify both of those things as well. A couple of hints for success. When you are justifying, you never want to use pronouns. So do not use the word it and do not say the graph. You want to refer to the name of the function that's given. So if I'm talking about f prime, tell me something about f prime specifically. Now, another typical prompt that we often see that builds these types of questions in is when we are given an accumulation function. So just like we practiced finding the derivative of an accumulation function, the reason we did that is because those are often the prompts that lead to the types of questions we just saw. So these three questions would be the same questions you might get asked about this type of equation. Now you'll notice here, we can tell that this is an accumulation function because g of x is equal to the integral of a different function. Right away when I see that, I like to get in the habit of finding the derivative, which would just be f of x, and finding the second derivative, which would just be f prime. I find that listing those pieces of information at the beginning of the question always kind of set me up for success, because at some point it's going to ask me, where is g increasing? In which case I need to look at g prime, which is just f of x, which happens to be the graph that I've been given. So I think kind of doing that work at the beginning can help set us up for success here. Now, here, justifying is really where it gets a little tricky, because you always want to show a connection. You always want to show a connection between the two functions. So you can't just say g prime. Your justification should have something like because g prime of x, which is equal to f of x, is greater than or equal to 0, for example, to justify where your g function is increasing. In your justification, you want to show a connection between g prime and f, which in this case for increasing would have to be greater than or equal to 0. Obviously, this part of the answer would change depending on what you're justifying. You also always want to show all your work. I know it seems like obvious. Yes, of course, you should show your work, but showing your steps can help you demonstrate an understanding of calculus ideas, which oftentimes on the AP test will earn you partial credit. The most common mistake that I see in these questions is that students assume that g prime is just f of x. You don't want to assume that. Always go back to the fundamental theorem and the original function. So for example, if g of x was 3 plus the integral from 2 to f of t, 2 to x of f of t, then g prime would be 3 plus f of x. So you don't want to just assume that the derivative is always f of x. It's not always f of x. All right, we are going to give you guys some practice questions. Thank you so much for watching. And again, feel free to reach out if you have any questions. I'm happy to go over them with you. And I hope that you have a great day.